station here.
Someone who's not working.
So do work on making sure you guys understand the normal hemoglobin saturation curve. If not, come see me on Saturday or before class next time. And then how pH affects that saturation curve. Excuse me. How temperature affects that saturation curve as well. And then the comparison of fetal to adult. It's the same idea, right? We have a left shift for the fetus compared to mom. That tells me that compared to mom, the fetus will have a higher level of affinity for any particular PO2 value I decide to look at with those. And that's because it has to be able to get oxygen from the placenta to deliver it to the fetal tissues. Well, we have to talk about carrying all that CO2 that your mitochondria are cranking out due to photophosphorylation and oxidative processes. What is blood mainly comprised of? Boy, that was a slow response, right? Water, okay. Now, we know that these gases have a solubility issue. So there's only two ways we transport oxygen. All right, this slide's about CO2. There's only two ways you guys transport oxygen. One is dissolved in plasma. The other is bound to hemoglobin. Those are the only two ways you're going to be able to transport oxygen. And there is a slide coming up to kind of remind you of that idea. But I've got three ways of transporting carbon dioxide. Now, different books are going to have different values for these concepts. That's nice. All right? This is your Bible. This is what you will memorize. All right? So don't go by any other person's book. We're going to pretend they don't exist. We're going to use these values right here. And we got to think about why it is that the majority of my carbon dioxide is actually transported not as CO2, but as a bicarbonate ion. Because bicarbonate is kind of a hidden CO2. So you guys are going to memorize this equation. It's going to become your favorite equation because we're going to see it several times throughout the quarter. CO2 plus H2O is going to give you carbonic acid. And that can just dissociate into a hydrogen ion plus a bicarbonate. You'll memorize this because you're going to use it over and over and over and over and over and over and over again. It's spontaneous. Enzymes make it go faster, but it'll happen by itself. So now when I look at this, I know that CO2 is fairly soluble, and I know that roughly, right, 7% of my CO2 is dissolved in my plasma. Right? Do not say 7% in blood, because hemoglobin is in blood as well. Right? You're going to get kind of mixed up. 7% is dissolved in my plasma, because plasma is mainly water. What do I do with that 8%, and that 9%, the 10%? What do I do with all that extra CO2? I need some way of being able to transport it. Well, the CO2 that is in your plasma can react to the water of your plasma, whoops, and form this, because this is not CO2. But I can see in there, there's a CO2 hidden in there. And so as I create CO2, some of it will be dissolved in plasma, but some of it will react to the water of the plasma and then become a bicarbonate ion. And I can carry a hell of a lot of bicarbonate ions compared to dissolved CO2. I can handle 70% of my CO2 production in the form of bicarbonate ion. I can handle 23% bound to hemoglobin. Do not say bound to a protein, because I get paid big bucks to misinterpret that. I'll say, oh, so you mean an antibody, because they're proteins, right? A muscle cell, they're made out of proteins. So make sure if you say the word protein, then you go comma, right, hemoglobin. I would simply just avoid the word protein, simply just use the word hemoglobin directly. 70% bicarbonate, right? 23% bihemoglobin, and 7% dissolved in my plasma as a dissolved gas. That could be an easy 6 points, who knows? Right? This is how CO2 can generate hydrogen ions. There's a topic you guys probably loved in chemistry. Stoichiometry And the Chatelier's principle, the more CO2 I have, bottom line, what happens to the level of hydrogen ions? Boy, that was scary, right? Do you all agree it's gonna get more hydrogens? Because you got more reactants, you get more product. It's that simple. Because you're mainly water, so this is not a limiting factor in my equation, right? More of that means more of this. More of that, what happens to my pH?
Goes down.
The pH go up or go down, the more hydrogens you guys
Goes
have.
down, goes down.
Right, you should all know this reflexively by now. More hydrogens means a lower pH. That might come in handy to understand. So here's the picture you don't want to memorize, but you do want to be able to look through it and go, okay, that makes total sense. That's what John just said. We could look at the top one up here, gas transport. Get your bearings, like where the heck are we? Going, oh, alveolar capillary, so this is probably then a pneumocyte type 1 cell, right? And there's my lungs. So I'm currently delivering CO2 to my lungs. Where did that CO2 come from? Oh, it came from the cells. So there's CO2 from the cells, dissolving in my plasma. There's CO2 binding to hemoglobin, and then there's CO2 in the form of a bicarbonate ion. There's my 3 ways of transporting CO2. Come down over here for the lungs, right? There's my alveoli. Apparently, I can transport CO or O2 dissolved in the plasma or bound to hemoglobin. That's going to be about 3%. You only hold about 3% O2 in your dissolved form. That means most of it is carried by the hemoglobin molecule, which we now know will change its ability to hang on to oxygen based upon PO2 values, based upon pH levels, and based upon temperature. It will all influence hemoglobin's ability to hang on to that oxygen. All right, now we're getting into Alice in Wonderland and the rabbit hole. What I'm about to tell you is now up for a big quandary. No book has the same information all the way through it. Your book, McKinley, has a statement in the end of the paragraph that says, this is contradictory to every other textbook that's out there. He gave no reference citation. I don't know what paper he read to come up with this idea, so I can't trust him. When I checked my 2019 respiratory physiology textbook, it did not say what McKinley says. It says what my other textbooks say. So either McKinley is on to something nobody else has figured out just yet, or he's not reading his papers correctly, but he might be right. So in the back of your mind, you say that my author might be correct, or he might not be correct. So we're going to go to a default kind of a generalization conversation here. The first part of this generalization is, go back to your 241, go back to your brain stem, go back to the medulla oblongata. And in there we had these nuclei. And we had one for the cardiovascular system, and we had 2 for the respiratory system, known as the DRG and the VRG. The argument is which one of those 2 is actually responsible for starting your normal pace of breathing. Most books say it's the DRG. That's the one we are going to claim. All right, the DRG is responsible for your normal, basic breathing pattern. The collection of the DRG and the VRG as a group is known as your respiratory rhythmicity center. It's your pacemaker for breathing. So that word in orange, right, is these 2 things here. So if I ask you what influences the respiratory rhythmicity center, don't say the DRG and the VRG because they are the rhythmicity center. Right, that'll make sense in a moment. They have their own pacemaker ability. Just like the SA node. They will spontaneously create action potentials, all by them lonesomes. And they're going to send a nerve impulse down your phrenic nerve. You guys remember where the phrenic nerve goes to? It goes to the diaphragm, right? We're going to put the first row in the back row from now on. You guys are just too fast for me, right? So the DRG sends a signal down the phrenic nerve, cause the diaphragm to contract, and you guys inhale. Now, the other group of nuclei, right, are called the ventral or the VRGs. So here's what I want you to do with this one slide. First of all, to control breathing, I've got two major parts of my brain that play a role in breathing. One is the medulla, the other is the purple pons. All right? What color is the rhythmicity center on the slide? What color is it?
Orange.
What color is the medulla? They probably go together, right? Because it's color coded. So the medulla has the rhythmicity center in it. And I remember from 241, that's where my DRG and VRG are located anyways. I didn't leave John to color code it. Now, let's go to this one. Because I love diagrams. That's nice. Just look at it as a way to visually bless you and to visually recognize that I can see that the DRG and the VRG are found in my medulla. That's all I want you to use this for right now. Just that one idea of where it physically belongs in the brainstem. Nothing else. Okay, now let's get to the other part. We know the DRG is involved in inhaling, right? Your normal resting breathing, like it says in green, right? Your normal everyday eupnea. Functions in quiet breathing, right there. All right, we'll get to the forest in a second. Now, what does the VRG do? Functions only in forced breathing. It doesn't play a role in passive breathing, only forced, which means forced inhalation and forced exhalation. The DRG just plays a role for the moment and just relax breathing in. Now, if you want to breathe forcibly in, of course the DRG has to be involved as well, because it's sending signals on the phrenic nerve. So the VRG will talk to the DRG and say, hey, get off your butt. Make John breathe harder when he inhales. That gives us the DRG and the VRG, which are parts of your respiratory rhythmicity center. Now let's go to the pons. I remember from 241, there are two groups of nuclei in the pons. You want to practice, please practice the spelling of these. You guys killed me on the final. Right? Aponeusic and pneumotaxic. You got to practice spelling them and maybe even saying them, right? Aponeusic, pneumotaxic. I realize that they are nuclei in the pons. I know they play a role in breathing. What is the role that they're going to do? Well, I underlined it for you. Adjusts the output of respiratory rhythmicity centers in the medulla. Regulating respiratory rate and depth of respiration. In other words, how fast and how deep you breathe is influenced by the aponeusic and pneumotaxic. You have to remember that the respiratory rhythmicity center, right, are these two things. So if I were to ask you to name the nuclei that influence the respiratory rhythmicity center, you don't list the DRG and the V because they are the rhythmicity center. You're going to be naming what? The aponeusic and pneumotaxics, because they're the ones that influence the respiratory rhythmicity center. And how do I know that? Because John wrote it for me on the slide and he underlined it. So I won't miss it. It might be on page 3 for 2 points. You never know. And this whole conversation is what is in dispute. What do the aponeusic pneumotaxic really do? What does the DRG and VRG really do? All right, that's where your textbook of McKinley really goes against the grain. It goes upstream compared to everybody else going downstream. So we're going to go by this, what I have for you in the slides, until somebody else definitely has done enough research and published enough papers saying, no, we actually now realize we're totally wrong. Back in your mind, you go, oh yeah, Moffat reminded me of that possibility 10 years ago. And so now maybe it might be true in 10 years. But out of all my textbooks, none of them say what McKinley says. They all say what my other authors say. So maybe he's right, just gotta wait and see. So we're gonna go with this, until otherwise confirmed. All right, let's look at some factors that will influence your respiration rates. So there are other things that talk to the DRG and the VRG, and there are things that talk to the aponeusic and pneumotaxic. Just to see, don't learn the path. But if these are my respiratory rhythmicity centers, and there's my aponeusic and pneumotactic, my pons, right? See how they have these chemoreceptors sending messages to the VRG over here, and the DRG, and here's more chemoreceptors and baroreceptors, right? Sending messages to my respiratory rhythmicity center. You need to figure out how these guys, or at least not how, but what they're doing to the respiratory rhythmicity center. So let's, talk about what are called central chemoreceptors. The name tells you what they are sensing, right? Chemicals, not pressure. Where do I find my central chemoreceptor? Well, think about the way to remember this. What are the two major divisions of your nervous system? What are the two major divisions of your nervous system? Central and peripheral, right? So where might I find the central chemoreceptor? In probably the central nervous system. Specifically and only in the medulla oblongata. You find it only in the medulla oblongata. I now also want to stress this with you guys. You must now always say medulla oblongata. You can no longer say medulla. Oh, shut up. Right? That's because you guys already know two different medullas, right? One's in the adrenal gland. You're going to have a third one coming up in the ovaries. Right? So you got to say which medulla we're talking about. Now, there's a nickname for the central chemoreceptor located only in the medulla oblongata. It's known as a hydrogen ion sensor. That's the name you want to focus on. Because the name tells you what it senses. What is it sensing? Hydrogen ions. That's cool. It's going to be helpful. Now, the other major chemoreceptor are the peripheral chemoreceptors, because they're found in the periphery, right? These guys will be found in your aorta, the arch of the aorta, top of the aorta, your carotids, because where do the carotids lead to? What really kind of important organ? The brain, right? So I want to do O2 quality control, the blood going to my head. The aorta can do quality control for the rest of my body, right? But I want my head and body kind of quality control. And that's the job of the peripherals. Now, when you read about these in your books, most books will say this about both the central and the both the central and the peripheral chemoreceptors. They will monitor your PCO2, your PO2, and your hydrogen ions. That's true. But we're going to zoom in on what they specialize in, right? The central specialize in their nickname, hydrogen ions. The peripherals will respond to significant drops in PO2. Significant drops in PO2. That's going to really trick their trigger. And they can get really excited and send lots of messages. Now, before we go any further about the central chemoreceptor, right, mainly keying in on hydrogen ions, that will indirectly talk about the level of CO2. So when they say that the central chemoreceptors monitor CO2, yeah, they're right, but they do it in a very indirect way. They're actually measuring the level of hydrogen ions as a consequence of the level of CO2. That's why you want to know this. I measure this to talk about this. If this is high, that has to be high. If that's low, that has to be low, just by the laws of chemistry.
So it's effectively a pH sensor, not
Well, that's what hydrogen ions are, the protons are, right? They modify the pH of the environment.
make sure you're not getting out of the buffered pH range that you want the blood to be.
Yeah, no. You'll see why later today, maybe. All right, but we're going to put a no on that idea because of the word blood you just used. Okay? We'll get there. All right, now, the baroreceptors, right, are going to measure pressure. That's easy because they're a barometer-like thing. So it's a really easy rule. Where do I find these baroreceptors? Well, in the carotid and the aorta. Same place I'm going to find my chemoreceptors. Right next door are your baroreceptors. And they respond to changes in blood pressure. And they're gonna talk to your respiratory centers. And here's a simple little rule. When blood pressure falls, respiration rates increase. That's just the rule. When blood pressure falls, respiration rates increase. So what's gonna happen if blood pressure rises? Respiration decreases. Yeah, it's just the opposite. Learn one, understand the other. That's a simple little thing to memorize. All right, so let's talk about which gases we are more sensitive in. If I were to ask you, all right, I know I have this thing called the respiratory rhythmicity center in the medulla. I know it's comprised of the DRG and the VRG. I know these little buggers called aquanucleus and neurotaxic, and all four of them are there to help control how fast I breathe. And I know I've got these things called chemoreceptors that measure levels of O2, CO2, and hydrogen ion pH values. So given all that, which are we more sensitive to? Changes in O2 or changes in CO2? You would think changes in O2 because we need O2 to survive with, but we're not. And here's how I can prove it to you. Your friend, the graph. Right? Graphs say a lot, everybody. Right? I'd rather look at graphs than read a book. All right, x-axis is what? Arterial PO2 values. Now, this is not a hemoglobin saturation conversation. This is now about what's on the y-axis.
Ventilation.
Okay, so now you got to remember this. First row, be quiet. What is on the y-axis? And does the y control the x, or does the x control the y?
X controls the Y.
X controls the y. So when I look at this, ventilation rates aren't determining my arterial PO2s. Since X's control the Y's, what it tells me is that my arterial PO2 influences my respiration rates. That's what the graph says. Now, look at the scale on the x-axis, right? Even in my mind, I could add 130 right here, right? And I have this nice little graph that shows me that for these changes in PO2, arterial PO2, as my O2 levels drop and drop from 130, maybe to 120, maybe to 100, maybe even to 80. Do I really have a significant change in ventilation rates from 130 all the way down to 80? No, you're looking at maybe half a liter a minute. But that's a whopping change in PO2. I went from 130 to 80. That's a 50-unit change. Where do I notice a significant change in ventilation rates based upon my PO2 values? At what PO2 value? Is that a significant change?
No.
Is that a change?
No.
Is that a change?
No.
It's like 60.
Maybe, but really right there, bingo.
60.
That is your significant change in O2 values. Now I start getting ventilation rates to increase. With every corresponding change in O2, I start getting changes in ventilation. This is, well, yeah, it's a change, dude, but it isn't much. So I can go from 130 all the way down to, let's say, 70 without experiencing significant changes in ventilation rates. Let's compare that to the next graph and then bounce back and forth. First of all, look at the range of values, right? From 0 to what? 130. In units of what? 20s, right? Okay. Now notice the scale on this graph. It's a lot smaller, isn't it? And my units are now, they're 4s, not 20s. Probably a more sensitive graph, indicating that we are less tolerant or more noticeable of teeny tiny little changes. Now, when you look at this graph for O2, couldn't we say that basically I could that's kind of like a plateau almost? Kind of a no change in ventilation with significant changes in O2? I could maybe kind of fudge that a little bit. It's a pretty flat line. Can I say the same for this? Right? There's no plateau-like part, right? For every change in CO2, you get a change in ventilation rates. As my CO2 levels increase, this is where calculus comes in. Right? Every single change in CO2 causes a change in ventilation because the X controls the Y. Now, is there any correlation to CO2 and this? How come they look kind of similar? Because can't this come from that?
Yes.
Can't my CO2s influence the level of hydrogen ions? So their graphs should look fairly similar. This is definitely more of a linear relationship, where I'm definitely saying, you gotta be careful, you got two things here, right? That is my plasma level of hydrogen ions, right? And my nanomolar per liter values. So the concentration of hydrogens is getting greater. Down here is the pH value, which also agrees with that, right? Because lower pHs with higher concentrations of hydrogens. Whether I want to look at the concentration of hydrogen value or the pH idea, as I become more acidic, I get increases in ventilation rates. Because I want to throw off, I want to exhale that CO2 out. Because if I can pull CO2 this way, I can lower my hydrogen ion concentration. So you can use respiration rates to alter blood pH. If you hold your breath and you don't ventilate, what happens to the level of CO2 in your blood if you're not getting rid of it? Isn't it going to increase? Because cells are keep generating, they keep making it, right? So according to that idea, what happens to your blood pH? It begins to lower and lower and lower, right? Which is why if you hold it as long as you can, and you start to breathe right afterwards, you breathe normally? No, you're breathing hard and deep, right? To throw off all that CO2 because you have an excess amount of hydrogen ions. If I can pull the equation this way, if I can get rid of these, right, I do a left shift in my equation and I draw the reaction to go this way. So these guys hook up to form carbonic acid. That breaks down to form water vapor in my breath and the CO2 in my exhalation. I can help lower that concentration by doing that. So now, just humor me. Who's in control on this graph? Ventilation or PO2? Who's in control on this one? CO2. Who's in control on this one? pH or hydrogen ions, right? So those three things are all controlling your ventilation rates. Who's in control here? I just switched it on you. Who's on the x-axis? That's always your boss. Ventilation now is influencing O2 and CO2, right? You just got to read the graph, right? But it makes sense. Here's ventilation rates, right? Low breathing and high breathing. Let's just pick the green curve representing the level of CO2, and let's have you breathe slower and slower to the point where I'm not even I'm holding my breath. Right, so you have a big tidal volume of, no, let's do it, it's expiratory reserve. And I hold it. This is gonna make me dizzy. Is my heart still beating?
Yes.
Okay, is blood still moving?
Yeah,
Am I still doing external respiration?
yeah.
Yeah, right. I'm dumping CO2 into my lungs, pulling out my O2 as the blood goes by, going down to my cells. They're delivering now less and less O2 because there's less and less in my alveoli because they keep taking it away, and my CO2 level's increasing. Because I'm not ventilating, right? I'm actually getting a little bit fun. This is a cheap buzz, right? So now, right? Why do I do this? What happened to my CO2 levels? They were up, right? How does CO2 influence ventilation rates? The higher the CO2, the more I breathe. Why am I breathing so fast? Because if I breathe fast, I can lower my CO2 values. And if my CO2 values are increasing because I'm holding my breath, I'm probably getting a decrease in O2 because I'm not resupplying the air in my lungs. So they go hand in hand but opposite. With high levels of O2, you're going to have low levels of CO2. Now, also ask this. If I look at this level of ventilation right along in here, if I breathe any faster than 8, am I going to get a benefit in my O2 values?
No.
Not really, right? And this is going to be important, right? You guys have to pay attention to how they draw the graphs. If I were to ask you to plot the relationship between ventilation rates and O2 values, right? And you do that, I'm going to mark it flat out wrong. That's a linear relationship, right? You have to show what it is, which means you got to kind of come up and begin to taper off, demonstrating the fact that after this point, I don't care how much faster you breathe, you're not gonna get any more O2 into the system. Now, where is this O2 being applied to? It's your alveolar partial pressures. This is where you guys have your Henry's gas law. This is where you have external respiration, so I can get that oxygen and CO2 in and out of my blood at my pulmonary capillaries. That makes sense? All right, think about that, because I forgot to bring something to class, some of you guys might be a little bit interested in. I have to go back to my office and get, unless you guys don't want your exams back.
Yeah,
We
grab
want them.
grab
We want them.
You don't want them? Okay,
No, I want
I'll bring
them.
them next Wednesday then.
Hi,
You want them?
Good.
Oh, jeez. So you guys converse about this, all right? Check your notes, and I'll be back in about a couple of minutes. We'll talk about your exam scores, and then I will also hand them back to you guys. I won't hand them back to you, but I will make them available to you.